questions during the lecture, but please do so in the chat, and please keep yourself muted for the duration of the lecture. One of the organizers will communicate your question to the instructor, and of course you'll have the opportunity to ask questions verbally at the end. With that being said, we're very happy to have Rose Morris-Wright giving us a second lecture on art and groups. Whenever you're ready.
All right, thank you so much. I'm glad to be back. So yesterday we talked sort of summary about what art and groups are and some general questions. And today I want to sort of zoom in on what I'm calling algebraic techniques for studying art and groups. And then in the third lecture, we'll talk more about geometric techniques. But so these are going to be more algebraic and combinatorial things, things about how do I take a word in a particular type of art and group and, for example, maybe I can get a normal form for that word and use those kinds of things, sort of more combinatorial methods to answer questions about the art and groups. So a lot of this is based actually in properties of the Art and Monoid. So I'm going to start there. So the Art and Monoid is exactly the same as the art and group, except it's a monoid instead of a group. I can spell monoid. There we go. So this is usually denoted a gamma plus. So just to remind you, remember this gamma is my graph. That's whoops. Did you guys lose? Yeah, okay. Sorry about that. It's taking a moment to come back. Where was I? All right, I guess I'm going to write this again. So the Art and Monoid, as I was saying, is basically the same as the art and group, except it's a monoid instead of a group. So here I have a gamma plus, and I'm going to have the same presentation, right? So I still have the set of generators are the vertices in my graph gamma. Remember this gamma is a graph. And then the edges in the graph determine the relations, right? So I still have this SI, SJ, SI relation equals SJ, SI, SJ, right? I'm alternating in the opposite order. And here the number of terms, the length of each of these words is determined by the label of the edge. This is Mij terms, right? Where in my graph gamma, I had like Si and Sj, and I had Mij was the label on this edge between these two. Right, so this was the presentation for my art and group that we learned about yesterday. And one of the algebraic things that we want to know about for learning about these groups is this monoid, which is just the monoid with the exact same presentation. So now I'm allowing words with positive letters, positive powers of letters, and not, I've forgotten that the SIs are invertible elements. And this monoid actually has some really nice properties. So good properties that the monoid has. And these are by Breescore and Saito in 1970. I can't remember if it's 72 or 73. We'll just say 72. So one of the nice properties is that the monoid has well-defined word length. Right, so every, or maybe let's call this well-defined length of a given element, maybe. So this comes from the fact that here in my presentation, I have a word that's equal to another word, and these two words are the same length. So anytime I have an element, or I have a word representing an element, if I can change it into, the only way to change it into another word representing the same element is to replace, subwords by another subword of the same length. So all of the subwords, all of the words representing a single element will have the same length. And this implies that the monoid word problem is solvable. Remember that the word problem is one of our open questions in general for groups. These are good properties, for the monoid for all A gamma. So this is nice. And then the second property that I want you to keep in mind here is that there's something called the prefix order, which is basically we can put a poset on the monoid elements. So given A and B in my monoid, I'm going to let A be less than or equal to B if A is a prefix of B, right? So if there exists some C in my monoid such that A times C is equal to B. So this is pretty basic idea. And the great thing about this is that this is a GCD order, right? So that means that any A and B in this monoid have a greatest common divisor in terms of this order. So this order isn't necessarily a lattice, but I am always going to get these greatest common divisors. And these two properties are great. They make the Art and Monoid pretty easy to study. So then one question is, how do I take this information about the monoid and translate it over to the group, right? Because we really want to study the group. All right, so question, how does this monoid relate to the group? And unfortunately, there's not a whole lot that we can do here. So one result is from Lewis Paris in 2002. He proves, so again, this is it's exciting. It sounds very simple, but it's exciting because it's for all A gamma, which we have very few results that start that way. So for all A gamma, the natural inclusion A gamma plus into A gamma is injective. So that's great. But there's not a whole lot else known about this relationship between the monoid and the group. For example, you could ask like geometric questions, right? You could ask like this monoid defined, like I've in my Cayley graph for my group, maybe I might have all the collection of monoid elements might define a subgraph. I could ask, is that subgraph convex? Is there, does it have any nice geometric properties? All of that is pretty much basically wide open, and I think are interesting questions there. But one of the main reasons that I'm bringing all of this up is that the monoid is really what's useful. It's sort of the basis for what's called the Garside structure in finite type groups. So now we're only 10 minutes in. We're already going to leave the realm of general Artin groups and restrict to finite type for just a second. So for A gamma finite type, we get some even stronger properties, which I will detail for you in a moment. For this monoid, and this gives us what's called a Garside structure. And the Garside structure is the main tool for studying finite type Artin groups. It's the reason that finite type Artin groups have, all of those questions that I was telling you about yesterday, where I said, here are a bunch of questions and we know the answer for all of these in the finite type case, and we don't know the answer in general, where they're basically all solved using the Garside structure. So I feel like I would be remiss if I didn't tell you a little bit about how this works. Yes, go for it.
There's a question in the chat. Does the embedding of the monoid into the Artin group make the Artin group ordered?
So first of all, this is a partial order, right? This prefix order. And it would give us, it gives us an order on like the monoid elements inside the group, but not necessarily on the group elements. Yeah, so you can do things like you can try and make some sort of like you can say, okay, well, I have a word in the monoid and I know where that is in my partial order. And then maybe I want to say like I have maybe now my group element is like a positive word times a negative word times a positive word, and I want to like have those be later in the order than the ones that are just like negative word times positive word. You can do sort of partial order things like that, but none of it really gives you a definitive order.
Thank you.
Yeah, good question. Yeah, no, this is a good, any other, this is a good place to pause for a moment here. So my goal for the next, at least the next first part of this is to just define the Garside structure for you and tell you a little bit about how it works, because I think this is an important thing to just know about for Artin groups. So how do Garside structures work? So I guess I should I should give you some. So these are kind of they're named after Garside in sort of the 1960s. He sort of started doing this, and then he sort of was studying finite type Artin groups and showed that they had a lot of these properties, and then a lot of the axiomatic structure behind Garside structures was defined by Paris and Dehornois in let's say the 1990s. Dehornois actually has like a whole book that's called Garside Structures, and you can go and read it. So this is going to be very, very brief. And then he defines what's called a Garside group, which is a group that has a Garside structure, and he proves all this stuff. But the main examples of Garside groups are these finite type Artin groups. We don't really have any other examples. So anyway, what is a Garside structure? So it consists of three things. You have a group, and you have a monoid, and you have a special element in your monoid, which is called delta. Right, so this is your group, and this is your monoid, and this is an element inside your monoid that has some special properties. So here are the axioms for a Garside structure. First, we want M is what's called atomic. So this means for every element in my monoid, there is an upper bound on the length of a word. This is called atomic because it, you can also phrase this as there are elements that are like the generators that can't be written by like they are always written by a word of length 1. They can't be written by longer words. All right, so M is atomic. M admits a prefix order. We've already talked about why Art and Monoids satisfy that. But not only is M going to admit a prefix order, but it's also going to admit a prefix order such such that this order is a lattice. So in other words, there exists these GCDs, and also there's going to exist an LCM for at least common multiple for every pair of elements in my monoid. And this is the main property that finite type Artin groups have and that infinite type ones don't have. This is where that sort of all breaks down. And then this, okay, so it admits a prefix order, and it also admits a suffix order. And which has the same properties. I'm not going to spend a whole lot of time talking about the suffix order. It's basically the same as the prefix, except the words are, it's the mirror image of the prefix order. And then we have this special element, right? So my special element, which is called delta, and it has these special properties. So when I conjugate an element in the monoid by delta, I also get an element in the monoid. So conjugation by positive words, I stay inside positive words. And then the prefixes of delta are equal to the suffixes of delta. These are called the simple elements. And these have to generate my whole group. So my generators in my standard presentation might be examples of simple elements, but there might also be more simple elements. Or you could have a Garside structure for like a different presentation of your same group. So let's see an example here. Because I know I just threw a bunch of abstract nonsense at you. So the classic example is the Braid Group. So this delta element is the half twist. I should draw this. Let's just do 4. I want to do something like this. I'm not the best braid group element illustrator, but it looks something like this. So you can sort of picture in your head, like I took my 4 strands and I just did this like half twist thing. And this happens to be equal to the least common multiple of the standard generators. And you get here, I think I saved a picture of this for you guys. Hold on. Here, let's make this picture bigger. So this is a picture of the part of my lattice of monoid elements, right? So here's my identity. These are my 3 generators of my braid group. These are like I just did one single. I should have drawn this picture closer to this. Here, let's just pull this picture down here so we can see it at the same time. So like this single cross and the other two strands are staying steady. That's one of these generators. And you can sort of see, like, if I go up this, like if this is sigma 1 and this is sigma 2 and this is sigma 3, let's see. one of these should be, oh, maybe I'm going up this way. Yeah, this should be sigma 3, sigma 2, sigma 1, and here I'm going sigma 3, sigma 2, sigma 1. And then I do sigma 3 again. Let's see. Sigma 1, sigma 2, sigma 3. Here's sigma 1, sigma 2. Yeah, so like you can sort of trace this half twist, up, and here you get your delta element as I add one of these at each step. And all these elements are all my simple elements. These are my prefixes of my, right, they're all below my delta element. And this picture is like inside my big lattice for my whole monoid, which is obviously infinite and goes off. So this is kind of the idea behind Garside structures. All finite type Artin groups have these Garside structures. Maybe we should write that down here. A fact. So this is partly, Garside, when he originally came up with this stuff, he was looking at finite type Artin groups. So this was sort of how he came up with this. And I already told you about Rees-Korn and Saito's paper. Right, so this says all finite type Artin groups have a Garside structure. Using the standard presentation. And this delta element is the least common multiple of the standard generators. So where does this all get you? Why should you care about all this?
This is dependent always on the presentation, right?
Say that again?
It depends on the presentation, the existence of the Garside structure.
The Garside structure very much depends on the presentation. And so one of the things that I was going to mention later, but we can mention now. So there's also what's called the dual Garside structure. For again, this is just for finite type Artin groups. And this is by Berman, Coe, and Lee in, let's see, I have a date in my notes here somewhere. 1998. Right, so this is like a different Garside structure, using a different presentation. They get a different Garside structure for the same groups. And so one of the big questions is, here's, let's call this question. So the standard presentation doesn't give a Garside structure outside of finite type. For infinite type, I can spell. I'm not doing very well with my spelling today. For infinite type Artin groups, basically because my set S doesn't have an LCM. So like our first candidate for this delta element just isn't there. Right, like maybe here, let's just do our favorite infinite type Artin group. Right, this like 3-3-3 example. Right, so like the least common multiple of A, B, and C here does not exist. you can get a common multiple of B and C, and you can get a common multiple of A and B, and like of each of the individual pairs, but you can't get a common multiple of all three of them together. And so this whole structure just breaks down, and you can't do this. And so one, question is like, are there other presentations that would give you a Garside structure, or even something that's like vaguely similar to a Garside structure. Even like maybe I'm going to relax some of these requirements. And the only results that I have outside of the finite type are these results by McCammond and Solway. McCammond also has like a really, on his personal website, he has like a really good survey paper about Garside structures and the geometry behind them, if you want to read more about this. But McCammond and Solway have what they call a Garside-like structure. So they've relaxed some of these conditions for what are called Euclidean type Artin groups. So finite type are also called spherical type, right? Because when their Coxeter groups are acting on a vector space, that vector space is spherical. And you can also get Euclidean type, which are, come back here. You can also get Euclidean type, which are these so for Euclidean type, so when Euclidean type Artin groups, when they act on this vector space, the vector space, the inner product on the vector space happens to be like your standard dot product. So this is like the closest thing that we have to this. But there's a lot of potential, I think, if you could play around with different presentations and find a Garside structure for more Artin groups. Let's see.
Rose, we have a question in the chat, and it's asking if different Garside structures for the same group are related.
They are related. Yeah. So like, or not necessarily all of them, but like there's a reason that this is called the dual Garside structure. They have sort of a relationship where you can go back and forth between them. And for a given Garside group, you can then usually get a dual Garside structure. But I don't think there really aren't any results about like limits on the number of Garside structures. Like there's no all of we have 2 examples basically, and there could be more out there. Who knows? But yeah, so I don't want to get too much into the details of the dual Garside structure, but yeah, they are related. And if you wanted to learn more, I would recommend this. Oh, why does my app keep doing that? Sorry, guys. Like I would really recommend that survey paper by McCammond. He does a good job of like talking about the original structure and the dual structure, and sort of showing you how the lattices are related to each other, and that's great. Let's see, we're at 12:30. Do people want to hear more about Garside structures, or should I go on to my topic for the second half of today? Topic number 2, I see at least one vote for it. All right, let's do that. All right, so okay, so this is sort of a new subtopic, but still in the realm of like algebraic techniques and questions about Artin groups. So this is what are called parabolic subgroups. All right, so we actually already talked about parabolic subgroups a little bit yesterday. We just didn't use this word. So I already talked about like if I have some subset of my generators, and I look at the set that's just generated by this subset, right? So this is the subgroup generated by T. So a parabolic subgroup is a subgroup of the form G, AT, G inverse for some element G in my group. So it doesn't have to be in the monoid, it's just in the group. So it's a conjugate of one of these subgroups that's generated by a subset of the generators. We already learned yesterday, maybe I'll just re-mention this result. So this is, so this AT and also its conjugates are isomorphic to a gamma sub T, right? So this is like the point is this is like a little Artin group inside my big Artin group, and it's the Artin group that corresponds to the subgraph that you would expect. This van der Leck, he also shows that like if I have A, T intersect A, R for some T and R, both subsets of my generating set, this is equal to A, T intersect R. So that's useful. But there's lots of things about parabolic subgroups that we don't know. And these are really an interesting thing, I think, to study because they're, right, these are like my little copies of an Artin group inside my big Artin group. So any chance for any sort of like hierarchical structure is probably gonna involve these. If you want to talk about like automorphisms of Artin groups, right? Like you're gonna have to take parabolic subgroups to parabolic subgroups. Like this is gonna be your tools for answering a lot of these big questions that we really don't know anything about. But unfortunately, even just like questions about these subgroups are pretty hard. So here's some questions. As I said, this mini course is basically just a list of questions. I hope that's what you guys are enjoying that. Okay, so here's question 1. So here let P and Q be parabolic subgroups. Question 1 is P intersect Q also parabolic? Ideally, these parabolic subgroups would form like a lattice inside my group. And there's some preliminary techniques. So the answer is yes in finite type Artin groups. I'm sure you guys have picked up on the pattern by now. This is by Completo, Gonzalez Meneses, Gebhardt, and Wiest. It's a pretty recent, I think this is like 2019 or 2020, something like that. And I also have by myself, but so this is just for FC type Artin groups. where P and Q are finite type. So that's a little bit more general, but still, not very much. And this is basically all we know about this question. And it's sort of, and I, to talk about a good use of the Garside structure, this paper by Completo and Gonzalez Meneses and Gebhardt and Wiest is like 20 pages long, just like technical stuff about the Garside structure. And this is their main result that they get. So this is the point is this seems like a simple question, but it's actually not. Here's question number 2 is are parabolic subgroups convex? Sort of in the Cayley graph, right? Can I if I take this subgroup, that will give me a subgraph inside my Cayley graph. Is that a convex subgraph? And the answer here is yes. Just for what are called these standard parabolic subgroups, just for where I'm not actually conjugating by anything. This is by Charney and Paris in let's see, I did write down the date here, 2015. But again, anytime you start conjugating by something, you don't really know what's going on. Here's maybe, let's call this question number 3. What are the normalizers and the centralizers in an Artin group? And this there's some sort of partial results for this by Cadell he has a sort of a series of papers in 2002 and then in 2003. These are both for finite type. And then in 2007, he starts talking about FC type. And he characterizes the normalizers and the centralizers of parabolic subgroups using what he calls ribbon elements. So the idea behind a ribbon element is that there exist elements in my Artin group such that maybe we should give, let's call them R for ribbons, such that when I conjugate R by some generator by this R, I'm gonna get a different generator, right? So conjugation by these elements permutes the generators. And basically, this means that I can have like a standard parabolic subgroup that's generated by like one part of my graph that's way over here, my defining graph. And then I can conjugate by one of these ribbon elements and get a parabolic subgroup that's being generated by generators in a completely different part of my graph that you would expect to be like totally unrelated in terms of the group. And so this basically makes things hard. Maybe I should draw an example of that. Like maybe if I have, it's nice to have like examples where your graph is like a kind of a long cycle, something like this. I don't really care how long it is, and who knows what the labels are? They can be whatever I want. And I can I could start over here with like S and T, and I can say, A, S, T, right? Here's my parabolic subgroup, and I can conjugate this by some element, right? Maybe I'm going to conjugate it. And I can get, maybe over here, I've got like A and B. So I can get the group generated by A and B. I can make this cycle like as long or as big as I want. So the point is that here that you have a connection between these parabolic subgroups that you would think are like kind of far apart inside your group, right? They're all of their, you know, the relations between A and B and S and T are free relations. So you would think that they would be very, very far apart from each other in whatever lattice you're trying to construct of these parabolic subgroups, but in fact they're the same parabolic subgroup, or they're conjugate to each other. So this is sort of part of what makes this studying these difficult. Let's see. And then the last question that I want to spend the rest of the time talking about, what question number are we on? Maybe we're on question 4. Is can we use parabolic subgroups to get some sort of hierarchical structure for Artin groups? So to construct I'm going to put it in quotes here, a curve graph for Artin groups. And if you're not familiar with curve graphs, I will give you a crash course in a moment. But maybe before do we need to pause for questions before I do that? We're good. Okay. All right. So here's a crash course in the curve graph. Let's just do curve graphs for braid groups. So curves graphs are something that are associated to mapping class groups and to surfaces. So this is very much a very specific version, but it's all that we need for our purposes. So the mapping class group of the n punctured disk is one of the ways that you can think about braid groups. It's a little bit different from the way that I've been drawing it with the strands crossing each other, right? So this is the set, or it's not a set, it's a group. It's the group of diffeomorphisms that fix the boundary of the disk and permute the punctures. Let's say this is up to isotopy. So there's some equivalence class on diffeomorphisms in order to make this group not just completely ungainly. Right, so your sort of picture that you should have in your head. Here's my punctured disk, right? And here's my element of the braid group. Maybe my element of the braid group looks something like this, right? And this element of the braid group, where I have like one twist, this is going to be the same as a diffeomorphism of this disk, where I'm like taking these two punctures and I'm sort of swirling them around each other, and you can think about like the disk is made of rubber or something. So as I like swirl them around each other, the surface of the disk like deforms with them and comes with them. And then so to study these, one of the main tools is called the curve graph. So the curve graph associated to this mapping class group, the vertices are closed curves. Again, up to isotopy. And then there's an edge between two vertices if the curves don't intersect each other. So maybe let's just draw like a very small subset of this graph. So like here's my my surface, right? And then there's going to be one of my vertices. I might also get like, here's another vertex, right? Those two aren't disjoint, right? So they're not going to be adjacent. But the purple one will be adjacent to this one because those two are disjoint from each other. So my curve graph will look something like this. It'll be green is adjacent to purple and adjacent to red. This is very, very small subset of my curve graph. So this is your crash course in this. And what are, like, why do we care about this? So the key properties, first of all, my mapping class group, which remember is just my braid group, acts on the curve graph in some nice ways. And a complete subgraph, a clique inside my curve graph in the curve graph corresponds to a free abelian subgroup inside my mapping class group. And we also know that the curve graph is a hyperbolic space. And this is one of the main tools that we have or I don't know, there's many tools that we have for studying mapping class groups, but this is a tool that we have for studying mapping class groups. Is delta hyperbolic is what I'm trying to write here. So one of the ideas, all right, so idea is we want to construct something that has these properties, a graph where the Artin group acts on that graph, and it has these properties. So we want to construct a curve graph for Artin groups. And the idea is that we want to use parabolic subgroups. Why would we do that? So the idea is that each of these curves is sort of defining like a smaller little disk inside my big disk, right? And it's giving me this hierarchical structure on my disk, right? And so parabolic subgroups are the smaller copies of Artin groups inside my big Artin group. So the parabolic subgroups are going to be our analogs of curves. And then we want to figure out what does it mean for two parabolic subgroups to be disjoint? Like how do I actually construct this? Oh, come back here. Where were we? All right, so that was your crash course in curve complexes, and now we should talk about how this works for Artin groups. So we're going to start with an Artin group. And you can do this definition for any Artin group you like, but we don't know very much about it except in very specific cases. So P and Q, again, are going to be parabolic subgroups. And we call P and Q disjoint if one of three things happens. If either P is a subset of Q, or Q is a subset of P, but not equal to, or P intersect Q is equal to the identity, and all the elements in P commute with all the elements in Q. So there's sort of two ways you can think about this. One is like, I really want this property that a complete subgraph in the curve graph is going to correspond to a Zn subgroup. So these properties are exactly, I'm sorry guys, I don't know why that keeps happening. And it always sends me back to the end of yesterday. Here, oh, and it didn't even, P is a subset of Q, but not equal to, or Q is a subset, but not equal to P, or they're disjoint, or as disjoint as subgroups can possibly be, and they commute. All right, so the idea here is I've got, I want P and Q together when I think of them as, you know, like their union isn't necessarily going to be a subgroup, but like when I think of them together, they're giving me a Z and subgroup inside my Artin group, right? So that's so this is our definition, and then so we define what's called the complex of parabolic subgroups. So the vertices here are they're proper, irreducible, finite type parabolic subgroups. I'll talk a little bit about why we have to put all of those conditions in a moment. And then the edges are, so I get an edge between P and Q if they are disjoint, as we've just talked about. So why do we need all of these conditions? So proper, these are all coming basically straight from, I'm like imitating what's happening inside the braid group. So proper, like inside the braid group, what are my curves? My curves, they're not isotopic like to the whole boundary or to like just a single puncture, right? So that's giving me proper groups. This is also what's helping me have my curve graph be infinite diameter, which is definitely something we want. Irreducible means that they cannot be decomposed as direct products. If I let there be reducible, then I would be constructing something that looks more like the multi-curve graph, right? I would be allowing for direct products of things. And then finite type, there's actually some debate about whether you should include this or not. Right, so finite type means that they are isomorphic to a finite type Artin group. And obviously, if my whole group is finite type, then this doesn't matter. I personally think that this should be included because this is part of what's helping me have this this category, this property where a complete subgraph gives me a Zn subgroup, because each of my finite type subgroups has a non-trivial center, right? So then the Zn subgroup that's corresponds to that complete subgraph is each of those centers now commute with each other, and I get this Zn subgroup. But if I allow for infinite type Artin groups, they're probably going to have trivial center, and so I'm not going to get this property. So that's why I think I personally think that should be included in the in the conditions, but there's some debate on that. And so this is sort of the definition of our candidate a curve graph. This is very much, sort of cutting edge. Maybe I'll just finish here. So like, here's some known. Oh my goodness, I don't know why this is happening. I'm so sorry. I'll have to fix it for tomorrow. So some known properties that these have. Like why do we think this is a good candidate complex for our potential candidate complex, our potential analog of the curve complex. So we have that the group acts on the complex the same way the mapping class group acts on the curve complex. That the action is just by conjugation, right? So any element in my group, I can conjugate every parabolic subgroup and get new parabolic subgroups. This is the exact same as the actual curve complex when A gamma is equal to a braid group, right? So it's very much generalizing that idea. It's also the same as what's called the extension graph for right-angled Artin groups. So this whole idea of let's come up with an analog of the curve complex is something that has been done for right-angled Artin groups. This is by Kim and Berda in I think it's 2013. And then even after they came along, there are also curve graph analogs just for like cat zero cubical groups in general that are known to be sort of related to this extension graph idea. But so this is this complex that we're constructing. We're generalizing two different things that are known to be the right thing in both of these categories. And we still have this, complete subgraphs, correspond to a ZN subgroup. So we still have that property, so that's nice. But sort of the unknown thing, the thing that we would really like, so is this delta hyperbolic? And this is like, I think one of the big questions currently.
So how nice is the action? Is it like a cylindrical, for example? Or?
I don't know if the action is acylindrical. That is another open question. Yeah.
Thank you.
Yeah, I would love to know the answer to that question. Maybe we'll end there as our continued adding to our list of questions. We'll have more of them on Thursday.
Thank you very much.